Welcome back to my favorite people, and thank you very much for watching this lecture video. In last lecture, I wanted to do a ring opening of epoxide under basic condition, and we reviewed the stereo selectivity and also radio selectivity for ring opening under basic condition. In this lecture, I'm gonna run a ring opening reaction of epoxide under acidic condition. Okay, so we do have ether, and any ether is going to have oxygen with two lone pairs, and so that lone pair, those two lone pairs are capable of taking acidic H from somewhere. If they get acidic H, now very soon we will have oxygen with a positive charge, and that's not going to be stable. Now, if we have a nucleophile, and the nucleophile, it can reach those two carbon, but in this case we have a primary carbon for both sides, and so there will be no technically selection or no difference here. The nucleophile just simply it can attack one of this carbon, and it will give us the final product. Say, for example, our nucleophile is Br-1. Where did I get it? I use HBr as an acid, so this is my acid, and H plus is taken by the ether or by the epoxide, and now we got that intermediate. Next step, we will have SN2 reaction, and our nucleophile for the second step, it will be the bromide. The bromide will attack the carbon from opposite direction, and it will kick the OH out of the system. The OH with a negative with a positive charge now is going to be a good leaving group. Okay, and now when I say leaving group, it's going to technically leave one of these carbons. Okay, it doesn't matter which one. Okay. So now what will happen if I change the acidic condition a bit? When I say change, I mean, for example, let's say we are using a diluted acidic version, or let's say we have an acid in the presence of, say, a methanol or ethanol. In that case, whenever you have plenty of water inside the solution, water will behave as a nucleophile, so you will get diol technically. But if you are using ethanol and methanol, and in that case, your nucleophile for the second step is going to be RO. So you will get ether plus alcohol. Okay, so we started from epoxide, we opened the ring, we got an ether plus alcohol. Okay, and as you see here, we have ethylene oxide and was treated with acid and diluted acid, and we got ethylene glycol. We got two OHs, and this is one good example for the first reaction. Okay, so the ring opening on acidic condition again is going to go through SN2 reaction. And because it's going to go through SN2 reaction, you will have some inversion with the stereocenter. And also, you need to ask yourself, like, how much steric effect we have, okay? So we will be dealing with the steric effect and also inversion with the stereocenter. Okay, and let's go through the steric effect first. Okay, say the attacked, so say we have an epoxide, that's our epoxide, and it has a primary and a secondary carbon. So there is no tertiary at all, okay? Primary and secondary. First step of this reaction, it will be something like this. Our oxygen had two lone pairs, use one of the lone pair to have a bond with oxygen, and now we have primary carbon and a secondary carbon. Okay, now if I zoom here, and the oxygen with a positive charge is attached to two carbons. One is a primary, second is a secondary carbon. The bond between oxygen and two carbons, those two bonds, I'm going to call them strong bond. Okay, strong bond. Okay, now what does it mean? It means when the nucleophile wants to be added to the system, it will not really differentiate much in, like, so strength of those two. It cannot differentiate much with the strength of those two bonds. To the nucleophile, both of them, they look strong. And now, if we cannot really differentiate them based on their strength, next factor, it will be the steric effect. This is a SN2 reaction. SN2 reaction, it prefers less steric effect. So between the primary and secondary carbon, the nucleophile will favor the primary carbon. So it's going to attack that one, and X will show up here. So we will have OH there, okay, and this is methyl, and X, it will be added from bottom of the molecule, and X, as you see, it will have an anti-position relative to the OH. Okay, X was added to a primary carbon, while the alcohol show up on the secondary carbon. Okay, now if you are adding acidic, let's say a protein to epoxide, while one of this carbon is a tertiary carbon, the story is going to be a bit different. Okay, and the reason for it is going to be this. So again, we will have O attached to two carbons. Here we have an H. There is a positive charge, and oxygen, it has a lone pair. We have a primary carbon and a tertiary carbon. Okay. Next step, when you add the nucleophile, let's say again, is going to be X, whatever. And this reaction is going to go through SN2 reaction. Okay, so again, similar to the previous one is SN2 reaction. But now I have a tertiary carbon versus a primary. Okay, tertiary versus a primary. And I'm going to say tertiary is more capable of handling positive charge because oxygen doesn't want it to have the positive charge. So what does it mean? It means this bond is not going to be really that strong bond. So instead of drawing like one solid line, I'm going to show it by a dashed line. And what does it mean? It means this one is a weaker bond. That one is a stronger bond. Stronger bond. Okay, now nucleophile is trying to reach the ring, and it will see one carbon with more substituent. Clearly, SN2 does not like more steric effect, but that bond is a weaker bond, and breaking it will be easier. Okay, listen carefully. We have a steric effect on tertiary carbon, but the connection between the tertiary carbon and oxygen is weaker than oxygen and a primary carbon. So what will happen in this case? In this case, the nucleophile will be added. Nucleophile will be added to a tertiary carbon. So X will show up here. This is the tertiary carbon, and OH, it will be on the primary carbon. Okay. So what compare it with the previous one? The previous one, alcohol was on the secondary carbon, the one with higher order. Here, OH is showing up on a carbon with less substituent or less order. Okay. And how about the halide? Halide here is on a tertiary carbon instead of a primary carbon. Okay, so I'm going to summarize whatever I did. Okay, we have two conditions. We are trying to run the reaction under, we are trying to do ring opening under acidic condition. Okay, if it's acidic condition, you need to ask yourself, what's the order of those two carbon? If there is, okay, if there is a tertiary carbon, the attack always is going to happen on the tertiary carbon. Listen carefully. If there is a tertiary carbon, regardless of whether there's a second part is a primary or secondary, always it will attack the tertiary carbon because the tertiary carbon is more capable of handling the positive charge. So I'm going to say there is more positive charge on the tertiary carbon. Okay. If there is no tertiary carbon, in that case, steric effect will be the dominant because we are dealing with SN2 reaction. SN2 reaction favor methyl, and then the primary. And the primary is faster than the secondary, and the secondary is faster than the tertiary. Okay, so if there is no tertiary, follow this order. Okay, follow this order, and I'm going to say primary, it will be attacking the primary, it will be faster than secondary, and so the attack will happen on the primary carbon. Let's practice some example here. We have this one is a secondary alcohol, a secondary carbon. Well, that one is a primary carbon. First step of this reaction, it will be generating this intermediate. So we will have H. H is going to go after one of the lone pair. And so now we will have H there. There's a positive charge on oxygen. Okay. Now, there is no tertiary carbon. Okay. Next step, our nucleophile, it will get involved. And what's going to be the nucleophile? This is going to be the nucleophile. Okay. I'm going to highlight the nucleophile. This one, it will be our nucleophile. It will be added to the primary carbon because we don't have a tertiary carbon. And the reaction here is a SN2 reaction, and it will prefer the primary carbon. So what I'm going to do, just simply take this, and I will add the nucleophile to the primary carbon. Okay, so let's add the nucleophile to the primary carbon. It will be added here, and we will have OCH3 there. Okay, now what will happen with the ring? This ring, it will break technically. And now I will have the OH here. And this is going to be OH. Okay, so as you see, alcohol showed up on the secondary carbon, and the attack happened on the primary carbon. Now, what was the configuration for this stereo center? We have 1, this is 2, and that one 3, and that's 4. So this is going to be our configuration. And now, how about here? 1, this is 2, and then 3 here. Again, this is our configuration. Why it still is R? Because we did the SN2 reaction did not happen on the stereo center. Happened on the neighbor carbon, and because it happened on the neighbor carbon, so it did not change the configuration of the stereo center. It used to be R and it stayed R. Okay, now I have a primary carbon and a tertiary carbon, and again I want to run the reaction under acidic condition. So the acidic condition, we will get this. First step, we will add H, and so we will take one of those lone pair and we will replace it by H. So here you go, we got an H there. Now there is a positive charge on oxygen, so oxygen is not going to be stable. Next step, we will add the nucleophile, and our nucleophile is going to be this one. Okay, so nucleophile will attack the tertiary carbon this time, because tertiary carbon is more capable of handling a positive charge. And so I'm going to add, the nucleophile here to this carbon. And so I will get OCH3 there. And again, what will happen with this one? Okay. In this case, we will have alcohol and oxygen, OH, it will be there. Okay, now, because this one, because this the attack happened on a carbon, on the tertiary carbon, and the tertiary carbon, it was a stereo center. Okay, this one is a stereo center, and the configuration for it is going to be, let's double check it, 1, 2, 3. So this one is a S configuration. The product should be R configuration. Okay, we had S, now it's going to be R configuration. The proof for it is 1, this, okay, 1, this one is 2, and that one 3, and that's 4. So the configuration here is R configuration. We had S, and now, okay, we had S, and we turned it to R. Why? Because the attack happened on a carbon, okay, on a tertiary carbon, and it changed the configuration of the stereo center. Okay, again, regardless of whether we are attacking the primary carbon or say the tertiary carbon, and always we will have inversion with the stereo center. Okay, always we will have an inversion with the stereo center. Okay, so here, okay. And so I have an epoxide, and in one case I have, let's see, we have 1, 2, 3. This is our configuration, and next one is going to be, okay, 1, 2, 3. That's going to be S configuration. So I got R and S configuration. Now I'm going to run the reaction under acidic condition. And but before I actually show you the answer, and we have this carbon. That carbon is attached to, let's see, attached to 1, 2 carbon. That's 2 carbon, so it will be secondary. Well, here we have a tertiary carbon, and so I'm going to say between secondary and tertiary, the attack will happen on the tertiary. So I should see the RO attached to the tertiary, and it will change the configuration to R configuration. Okay, again, this one, it will be R configuration because nothing changed on it. But the second one, and we're going to have 1. This is going to be 2, and this one, it will be 3. Okay, and that's going to be the 4. So the configuration is supposed to be counterclockwise. It's supposed to be S, but because methyl is pointing to us, it will be R configuration. So what did we get here? We got R configuration. Used to be S configuration, now turned to R configuration. So under any condition, whether we are running it under acidic or basic condition, we will have inversion with the stereo center because the second step of ring opening runs through SN2 reaction. And this is going to be the end of this lecture, and thank you very much.